That we have this idea of uniformly most powerful test and this monotone likelihood ratio, we can connect the two ideas together. Specifically, theorem 9.3.1 says if we have these hypotheses down here, an increasing monotone likelihood ratio function as a function of t, then we can get a uniformly most powerful test, or a UMP test, of the form where t is bigger than or equal to some threshold, where we reject h naught if this t is bigger than or equal to some threshold. This theorem specifically only deals with this situation, but later on in the book it mentions that, and this is an exercise in the back of the book, that you can actually have the reverse situation as well. So if your hypotheses were flipped and you have a decreasing monotone likelihood ratio function, a monotone likelihood ratio as a function of t, then you can construct a UMP test where you reject the null hypothesis if t is less than or equal to c. So both versions are totally valid. It's just a different version of this theorem, which was left as an exercise. So let's see this in action. Consider the exponential random data where we have this unknown parameter theta, and we have this hypothesis where theta is less than some value. Theta is less than or equal to 1/2 under the null hypothesis, and we have theta is greater than 1/2 under the alternative hypothesis. We have already seen that we have a monotone likelihood ratio as a function of t, where t is equal to negative y, which was equal to negative the sum of the individual x values that we got. We also saw that that was an increasing function of t. So this is a monotone likelihood ratio as an increasing monotone likelihood ratio. That's important. And we know by this theorem that if we have that situation, we have this one start up here. So we're in this territory. So we know we have a rejection rule where t is greater than or equal to some threshold. So if we want to construct a alpha test or a UMP test with level alpha, we know that this test is going to be this structure, reject h naught, fail to reject h naught if t is greater than or equal to c, and if otherwise. Now we want to pick c such that we have an alpha level test. So find c such that we have a level, I'm going to say alpha sub naught test. We can do that using the distributional properties of t. Now recall that y is distributed gamma in 1/2, which is the equivalent of a chi-squared distribution with 2n degrees of freedom if h naught is true. We can use this to our advantage. We want to have a level alpha naught test, so we're going to do probability, reject h naught, given h naught true. We want this to be equal to alpha, but we know that this probability is the probability that t is greater than c when theta is equal to 1/2, so theta naught is true, which is equal to probability of negative y greater than or equal to c, theta equals 1/2, which is equal to the probability that y is less than or equal to negative c, theta is equal to 1/2. And then we want to set this equal to alpha. Now, we can do this through integration, And with integration, we have this chi-square distribution for y. We are trying to find this value c, or sorry, negative c, such that we have 1 minus alpha over here and alpha over here. So alpha percent of the data over here. Now we can do this with integration. The other thing we could do is just use R code. So to do this in R, this would be, to get C, we would use Q chi-square, 1 minus alpha, degrees of freedom, is 2 times n. If n equals 10 and alpha naught equals 0.1, then we would find that negative c, which is what would come out of this function over here, or what we would do if we used integration, would be 12.44, or c is equal to negative 12.44. And plugging those values in, we would find that we have a UMP test in this setting.